Assalamualaikum and good day everyone. Today we will continue our chapter 4, 4.2 graph terminology. In the previous class, we learned about the adjacent until the integrate and out degree. So today we will cover about the bipartite graph and the subgraph. The lesson outcome for today is to introduce bipartite graph and introduce subgraph. Let's see the bipartite graph. A simple graph G is called bipartite if the vertex set V can be partitioned into two disjoint non-empty set V1 and V2. So every edge in G is incident with a vertex in V1 and a vertex in V2. We call the pair V1 V2 a bipartition of the vertex set V of G. The figure 4.2.17 and the figure 4.2.18 is the example of the bipartite and not bipartite graph. So how we need to know whether the given graph is bipartite or not bipartite graph? Let's see. Let's see how we want to check whether a given graph is bipartite graph or not. Let's see the example number 1. We have the figure 4.2.17 which is C6. We already learned in the previous class. Okay, the C6 have the 6 vertices and we have to draw our 6 vertices here. After that, we focus to the 1 point. Let's say we focus to the point A first. Alright, point A is connecting with the point B and the point F. So we need to write down the point B and the point F here. So we connect them with the edges. So we connect A to the B and the A to the F. So we already have point A, B and F here. So the next point that we need to focus is the point C because the point C is not yet in our graph here. So point C is connecting with the point B and the point D. So we just need to write down the point D here. So the point C here and the point D here. So we put the edges to connecting the point C into the B and the point C into the D. So the last point is the point E. So point E is connect with the point D and the point F. From here, from our graph, you can see that there are two disjoint set, two group of disjoint set. We can see that the ACE is the set for the V1 and the BFD is the disjoint set for the V2. So we have two different group here and we can see that from the figure that each vertex in the figure is belong to exactly one of the two set. There are no repetition. Alright. So let's see. Each edge connect vertices of two different set and no edges between vertices within the same group. There are no edges in the same group. There are no edges connecting the vertices within it. So it means that this graph is bipartite graph. If there is an edges, so this means that this is the not bipartite graph. So the final answer is let V1 equal to ACE and let V2 equal to BFD. So C6 is bipartite graph. You need to list down your complete disjoint set if it is the graph given is the bipartite graph. Or you can use another method to check the bipartite graph or not. This method is more simple. Alright, the step 1 is we need to divide the given vertex set into two disjoint set V1 and V2 and each vertex belong to exactly one of the two set and the vertices in the same set cannot be directly connected. And the step 2 is each edge connect vertices of two different set. If yes, then this is the bipartite graph. If this bipartite graph, so you need to list two complete disjoint set. If no, then if there is an edges that connect vertices of two different set, then this is not bipartite graph. So when it's not bipartite graph, so you need to state your reason. Let's see the example number 1. The solution, let's V equal to ACE and let V2 is the BDF. So every edge of the C6 connect a vertex in V1 and V2. So we can see that C6 is bipartite. Let's see example number 2. We let V1 equal to ACE and let V2 equal to BD. So we can see that A is connecting with the B and connecting with the D and also connecting with the E. So we can see that A and E is in the same group. So we cannot we know that we cannot have vertices that in the same group that are connecting with each other. So we want to say that the V1 is AC and the V2 is BDE. So we can see that the B is also connecting with the E. So there are no way to do that. There are no way to do the vertices is not connecting with each other in the same group. So the W4 is not bipartite. Since if vertices A and C in the V1, then B1 and D in the V2, vertex E cannot be either in the E1 and E2. So let's see the complete bipartite graph. Let G be a bipartite graph with V1 equal to M and V2 equal to N. If an edge run between every vertex in V1 and V2, G is a complete bipartite graph denoted by KMN. Let's see the example. Let V1 equal to AB, let V2 equal to CDE, and edge run between vertex in V1 and V2. So we have V1 here equal to 2 and the V2 here is equal to 3. So we know that the complete bipartite graph denoted by KMN. So we can denoted this figure 4.2.9 as a complete bipartite graph denoted by K2 3. So here is the exercise to test your understanding. I hope you can do that and check your answer with your lecturer. Next is the application of the special type of the graph. First is the job assignment. We have M employer and J different job. It is to model the employer's capability, and each employer trained to do one or more job. It is represented in the blue line, and the green line so the assignment of the job. This is the bipartite graph. So we are trying to find a matching in a graph model. A matching is a subset of the set of edge such that no two edges are incident with the same vertex. So the next application is the local area network. Illustrate the connection between various computer and device. Figure 4.2.23 is the star topology K1N with all devices connected to a central control device, while the figure 4.2.24 is the ring topology which each device is connected to exactly two others, while the figure 4.2.25 is the hybrid topology which is star plus ring. Its redundancy make the network more reliable. So next we move to the subgraph, the last topic. So the subgraph of a G equal to VE is a graph H equal to WF where W subgraph V and the F subgraph E. A subgraph H of G is a proper subgraph of G if H not equal to G. Let's see the example. The K5 is the example of the graph G equal to VE. So here is the subgraph of the K5. Let's say another example. We have three graphs here, G, H and J. So the question is, which one of these two graph H or J is subgraph of the graph G? So we need to find out with which one of the two graph H or J is the subgraph of the graph G. What we need to do is we need to see the vertices and also the edges. If the H have same vertices and the same edges with the G, so it is said that H is subgraph to the G. But we can see here that in the graph G that we have, we can see here that in the graph H we have edges that connecting with from B to the C, and in the graph G there are no edges that connecting from B to the C, so the H cannot be subgraph to the G. Okay, let's see the graph J. Okay, the graph J, we can see that it is the same, it has same edges, same vertices with the graph G. So J is the subset of the graph G. So the union of the graph, the union of the two simple graph G equal to V1, E1 and G2 equal to V2, E2 is the simple graph with the vertex set V1U, V2 and the edge set E1 union E2. The union of G1 and G2 is denoted by G1 and union G2. So we have the graph G1, graph G2. So we have G1 union G2 is the combination of G1 and G2. So here is your exercise 4.2.4 to test your understanding. You have 3 questions here. So I hope you can do it well. So that's all for today. Thank you. Have a nice day.